So great. Now before I get into it, I first want to give a little bit disclaimer in that this is something that maybe differs from a lot of work that you'll hear about in the workshop, is that this is kind of something that's like a little bit longer term. And I haven't really, there's kind of a lot of work to get it to something that might look like something that you build hardware for. And there's going to need to be a lot of new hardware techniques that we're going to have to develop in order to actually build something like this. And then at the end, I'll talk a little bit about kind of how to optimize some execution overhead that we're going to incur. Okay, so first off, let's consider a 2D platform where kind of my qubits live on some chip or something like this. And the current way that people think about building quantum computers is that you have universal control over each qubit. And what that means is that I have a kind of at least one control line going to each individual qubit that comes from the outside world, the control. And this leads to some problems because kind of the characteristic scale of one of these qubits is somewhere from, say 10 nanometers to maybe a few hundred microns. And the scale of the connectors to the outside world is something like millimeters. At the end of the day, some person has to go and plug in a wire into your device. And this leads to kind of some problem where, okay, you have some dense packing of your qubits, and then you have kind of some footprint for some pads that are where your connectors are going to go. And these pads are very large. So you have to kind of route them into my grid of qubits. And that's going to place some limit onto your size because these wires, you can only pack them in so tightly. Okay, so classical processors scale really, really well, right? A typical state-of-the-art classical processor has something like 100 billion plus transistors, where here maybe we should think of transistors as the analog of qubit. And something to note is that you do not have universal control over your individual bits or your gates. It's not like you have operations that you're just applying to your bits. So here's a picture of a not state-of-the-art processor. So this is something that would have been, say, from the 1980s or something like that. And the thing that you'll notice is that the majority of the functionality of the circuit is just something that's fixed at manufacturing time. Kind of, you have some pattern of circuitry of wires and transistors, and they're just kind of all coming together to actually make this device. And we actually have control over a very small number of bits of this processor. Kind of right here, these sorts of little pads that you see is kind of a wire that's going to the outside world. And in this device, there are probably something like 40 of them, right, to control something that maybe has something, I don't know, several thousand transistors at least. So there's kind of this kind of difference in scales between the amount of devices that you fabricate on the chip versus the amount of devices that you can actually control. We're feeding some voltages between this that are getting data into and out of our processor. So the general idea is that I want to get to is whether or not we can just copy this quantumly and build very, very large devices in a similar sort of fashion. And informally, the answer is yes. So what you can do is you can pick some global gate patterns that are picked at manufacturing time, and you have some constant number of qubits that you have kind of arbitrary control over, and you can be universal and fault tolerant. And roughly the way you might wonder, okay, well, how does this get me to a constant number of control lines? Is that kind of classically, you had this global clock signal. There's some globally driven dynamics. And then I had individual control over a few bits. And you might imagine something very similar if your qubits were sufficiently kind of identical in some sense. You would distribute a signal that is the Hadamard signal or something like that would execute your manufacturing determined pattern of, for example, Hadamards or something like this.
Sorry, can you explain again what you mean by manufacturing time?
Yeah. So what I mean by this is that at some point, you fabricate a chip, right? And what I'd like to do is I'd like to fabricate a universal processor. And this processor is going to have this global gate pattern. It's going to be capable of executing just that. And then I'm going to be able to like maybe some small number of qubits, just initialize these to computational basis states and like measure them. And that turns out to be universal and fault tolerant is what I'll show. Yes.
Can I just confirm these all on arbitrary default qubits? Those are physical qubits?
Yeah, that's right. Yeah, yeah. Now there's this problem of, well, okay, typically in these like solid state systems, my qubits are very much not identical. So this is where the new hardware techniques have to come in. We can imagine, for example, maybe you locally, because in order to get the benefit of being able to build very, very large systems, you need to have some system that is just fundamentally incapable of individual universal control. So you'd, for example, need to figure out some way to, for example, either make your qubits very tightly controlled in terms of the manufacturing variance, or you need to find some way to like locally tune it up without actually talking to the outside world. There's also some techniques from, like, for example, FPGAs and stuff like that, where you can kind of serially address these things, or serially address these particular regions of the chip in a very slow manner, which would be fine for calibration. Either way, you need some new technology. Yep.
How does the control wire scale roughly log n of the Pattison side, or?
So fundamentally, it can be a constant. It can be as little as perhaps 2 or 3 wires. Yeah. But then most natural choice is probably logarithmic in some sense, yeah.
And, classically, did it also evolve from fault connect historically that to local communication because they had pull-up?
So classically, I think that they were kind of always building sort of these, so at least at the point, once they got to the point where they're actually fabricating chips, it's very natural that you lay out your transistors, you connect them up with kind of wires that are in this metal layer, it's called, that you route them in. And, you know. Okay, good. Okay, so in terms of the feature of classical circuits that we want to copy, in a classical circuit, each component is wired to its neighbors. So, and then data kind of flows through these gates that are kind of fixed at manufacturing time. So here I've drawn an adder. So these are kind of logic gates that you might be familiar with, you know, AND gates and XOR gates. And then these components are what the classical computer architecture people call registers, or classical digital circuit people. And the idea being is that this entire circuit here is provided, each of these registers is provided this clock signal, which at the rising edge of the clock, it just takes the input here and then just copies to the output and kind of holds it. So kind of after, say, like 3 clock steps, any signal, you know, you have some inputs here, and then after three steps of the clock, you get the output, which is just the sum. So we want to kind of copy some similar idea here with kind of everything fixed, and then the data moving through these fixed circuits. These are registers.
So is it moving from one register to another?
That's right, yeah. So if I set some initial data here, at the first rising edge, this data is going to get propagated to here. It's going to flow through these gates. That takes some amount of time, but it's kind of something that kind of the system settles to that state. And then at the next rising edge, hopefully this is settled before then, you're going to get kind of the data copied, and you're going to proceed in steps to the computation. Notably, that by the time that the data has made it here, you can pipeline this computation in the sense that you can start on a second computation here before the first computation is finished.
Basically, is the clock connected to every transistor or
Good. It's connected to most of the transistors, not all of them. I mean, like essentially here, so this register here would maybe be implemented by like a few transistors, and each of these gates would be implemented by a few transistors. And so the clock would be, in this circuit, maybe connected to like 1 in 10 or something, for example.
So what's the point of having clock?
So you might say, okay, well, why do I need this thing? I'm just going to set these kind of these inputs and then just wait for the data to propagate through. Yeah, in some sense, well, it's actually just an engineering consideration. For us, it'll be a little bit more fundamental, but kind of the idea being is that you, if you have this, you have some delay for like to go from the input to the output, and you want to ensure that the data like has kind of settled right here in like this period that you have before like the next rising edge of the clock. So it kind of allows you to kind of isolate chunks of the circuit and ensure that each one has the necessary delay. Yeah, so it's just engineering. Okay, great. Okay, so we're going to copy something similar. And kind of the thing that we want is kind of a quantum wire. And suppose that I have some circuit. Here I've chosen to draw some brickwork thing. And it's laid out in 1 dimension. And then I have kind of time. Well, I can turn this into a periodic 2D circuit just by kind of, oh. Well then. Okay.
Any issue?
There's a missing figure.
Is it appearing in the computer?
Let me do this. Okay.
So, so the general idea is that you arrange kind of each layer of this circuit onto kind of a second direction, such that and this is a depth 3 circuit. So in steps 0 and 1, I'm just going to swap kind of qubits starting kind of from here to the next layer. And then in step 3, I'm going to apply kind of the gate of the circuit, for example, the 0th gate layer here, the 2nd gate layer here, and so on. And so the data, if I start here and then wait for, I guess in this case, 7 applications of the step 3 circuit, I'm going to end up with my data over here with this circuit here applied. And the point is that this transformation kind of preserves the fault structure of my original circuit. So if I had a failure of a gate, say here in the 3rd layer, that corresponds to an execution of this original circuit with some gate here that has failed. Okay. Okay. Great. So now let's build a memory out of this thing. So, okay, so first off, there exists one-dimensional concatenated code fault-tolerant schemes that have kind of completely local processing. And in addition to the processing being completely local, it's also actually completely quantum. You don't need any classical degrees of freedom, although you'd prefer it. And so these have been known since the 90s. Happy to discuss more about that. But anyways, once we have this thing, we can apply the previous construction that I called the tile transformation. And you can apply it to just like the error correction gadget, just the logical identity. And then you can take a few of these things and just kind of connect them up in a ribbon. And already you can see that this is going to be a memory. And well, we want something that's on a square or on a plane. And the reason being is that, well, we can't manufacture, or it's kind of hard to manufacture these like ribbons. And then furthermore, in terms of what's easy to manufacture in like 2D chip land, it's things that roughly fit in a square. Kind of the difficulty is like whatever your longest length scale is, because there's some optics that you need in order to actually like in the photolithography steps, to manufacture the device, you have some optics, and those naturally work in kind of a field of view that's square. So kind of the trick is to kind of fold this ribbon in a plane like this, such that we have quantum code blocks that are kind of propagating around the ribbon like this. And they kind of, once they hit the fold, they kind of change propagation direction. And so, okay, so that's what it looks like macroscopically. And from now on, whenever you see this kind of pink ribbon, think of something that's like a logical gate gadget from the 1D fault-tolerant scheme, and then the propagating data is quantum code blocks that are, yeah, and then any insulas that I need. Okay, so microscopically it looks like this. It's kind of a mess. But the idea being is kind of, you might have some qubit here, trying to trace it through, it hits the folds, and it starts propagating upward. Great.
So to propagate the information, basically, are you thinking of something like a swap or like some teleportation or like MBQC or?
Specifically a swap. And the reason being is that I can't measure because that requires a control line. Yeah. So it's the step 3 thing where I just keep swapping. In some platforms, you can like physically just move your qubits, and that's ought to be higher fidelity and such. Okay, great. Cool.
So except that the swap replaces teleportation, can I think of it as spiritually same as a MBQC or?
Almost. Well, okay, so this, okay, this part about not having the measurement is quite critical. Measurement and then the feed forward. The other thing is that in MBQC, you kind of like prepare out a cluster state and then you kind of consume it. You should, but we're actually going to use this fact that we have multiple kind of steps in the circuit to kind of propagate many code blocks at different stages of processing to get the best rate in our memory.
So through swap, what we want to propagate is a logical qubit, not the physical qubit, right?
Mm-hmm.
Okay.
Right, but kind of you arrange the qubits of a code block kind of in one slice. So, and swap is transversal.
Yeah.
And furthermore, it's transversal at every step of the processing.
How do you say the measurement part of the control line, like you know, in this chip where I don't have control into the boundary, can I just in the middle have a little thing that's autonomously doing surface code error correction, and it doesn't need, or, you know, it's just always doing error correction. It doesn't need to talk to anything. You don't need to tell it or use it. It knows what to do it itself. Like that shouldn't count as a control line, would it?
Yeah, that's right. Yeah. So if you're locally processing the measurement, then yeah, absolutely. Yeah. And indeed, there are kind of some technologies that might allow you to do these like local measurements. Yeah. Good. Okay, so that's already enough to get us a 2D memory. So this is the usual like threshold theorem statement. There exists an accuracy threshold and a family. We store some qubits that are logical qubits and some number of physical qubits. We arrange it roughly in a square by kind of doing some space filling curve. And we have a memory. And the kind of storage time of the memory is quite long. So great. And this rate that you get is actually kind of the rate of the underlying fault tolerance scheme up to some constants. So you can kind of preserve that rate, which is quite nice. Okay, cool. Oh, yes. And the circuit is kind of tolerant to fabrication errors in the sense that if you imagine that you have a broken qubit or broken gate, kind of you can imagine it as there's some location, on this ribbon or whatever that's just dead. But then in terms of the moving data, as my code block kind of passes that region, it always gets a failure on that location in that part of the circuit. But that's fine because from the kind of propagating code blocks perspective, that's just an error, and we know how to correct this. Great. All right, so I promised a universal computer, so let me build that for you. But first, I need to define for you some model of computation that I want to consider. And I need to be more precise about what I mean by control line. So think of it as I have some classical control box or whatever, and it's connected to some quantum chip or whatever by some number of wires. Now, some of these wires might be going out and being some distributed kind of operation, that's kind of my global signals. So for example, if I have some pattern Patamords that I need to do. And then there's a few qubits that are kind of somewhere that are controlled. And what I mean by control here is just that I can initialize them to 0 or 1, and I can just measure them. And then kind of the actual model is that the operator, they receive some description of the quantum circuit that they'd like to sample the output of. And they compile this into a string of instructions. Think of it as just a tape. Then they walk up to the quantum computer, feed the tape into the quantum computer, and then wait. And the quantum computer kind of produces for them some output tape. Then they take that output tape, they post-process it, and then they produce the output. And all these steps are efficient. So that's going to be our model.
What do you mean by quantum computing?
This device. So it's going to be this this kind of depth-3 circuit where kind of I get to control this small number of qubits. I get to decide what they do based on this input tape. Yeah, good. Okay, and so kind of much like in a classical computer, where in order for it to operate, you need to provide it a clock signal. We're doing it something very similar, where you need to kind of drive with this global circuit, which is in some senses identical. So then you can ask, okay, well, if I'm talking about circuits, how is this like universal in the sense of like, if I have like a fixed circuit? And kind of the general idea is that you need to reuse components. So classical processors, you'd be like, okay, yeah, that's a circuit. But actually, they're not quite the computer scientist circuit, right? In particular, they're kind of reentrant. They can kind of the output of the circuit can be fed back into itself. So, and then the actual like choice of what computation to perform is typically performed by routing the data through different circuit elements. So here I have two operations, A and B, and I have some data that I'd like to kind of perform, some string of operations like A, B, A, whatever. And what you do is you have kind of some control, which decides, based on if this is 0 or 1, which kind of side that the input goes to. So you might route it through operation B or operation A. And then you just need this one bit of control for something that's like, these operations themselves might actually be something quite complicated.
So is that thing before operation, can I think of it as a clock? Or
Think
a resistor and control line is a clock.
so. The way to think
I
about
don't know how classical computer is working, sorry.
So the way to think about it is that these registers that I showed earlier are kind of sitting interspersed like everywhere here, and so kind of this component here would be, just think of this as kind of like a switch, like a railway switch, where
But it says instruction is like some time-dependent signal generated by computer, right? I was wondering whether that is actually some different pattern of clock. I don't know.
So it's completely unrelated to the clock. Well, at least in the way that like kind of
Or something on top of clock.
Yeah. Kind of think of this
Cascade.
clock as kind of something that's happening in the background, like always, and then you're feeding in the like instruction signal, of course, in time with the clock.
Okay.
Yeah. So, okay, great. Well, let's copy that. So suppose that we have some stream of noiseless control bits that are encoded in my quantum code, for which I have this 1D quantum fault-tolerant scheme. And then I have some tape that's just like circulating around, right? Well, I can do exactly the same thing, which is if I want to do a Hadamard to some qubit circulating on my tape, I would kind of set a 1 kind of passing on the control bit, which would swap this passing logical qubit over to this tape here. I apply the Hadamard gadget, and then I swap it back. So then I can now, you can imagine how this already is enough to get you some amount of control over this memory tape. There's actually a technical ingredient, which is that if we have this tape, which is kind of this long kind of string of propagating code blocks, we need to make code blocks that kind of pass by a particular point on the chip at different times. We need to couple them in some way. And the way to do it is we need to change their propagation speed. And this is a bit of technical detail, so if you like, you can just ignore it. But the general idea is that we're going to skip over some site in this that microscopic implementation. So that's kind of what it looks like, is we just introduce some kind of slightly longer swaps, still constant size, and we just skip over step. And so if I have 2 of these tapes with one of them being kind of this kind of fast forward operation and one of them being the regular operation, then kind of if I had two propagating code blocks that were kind of at slightly delayed, this kind of brings this one up to speed. Okay, great. So this is enough. So we're going to implement just a minimal gate set, which is implement Hadamard on like 1 qubit, controlled swap or controlled phase on 2 consecutive qubits, and then noisily measure a qubit, write it to the output tape, and replace that by a 1. And then you kind of take these operations and you just stick it onto the memory tape. So that's what it looks like. I haven't told you where these control bits come from. I'll get to that later. But kind of here it is. Here you can kind of see this is kind of the messiest bit, but all this is doing is it's just picking off 2 consecutive code blocks that are propagating on this memory tape, kind of bringing them in line, performing the operation, and then kind of putting them back to their original places and then putting it back. That's all. And so now I need to tell you where these control bits come from. And this is kind of the actual, like, little bit of where something fun happens. And the first thing to note is that, okay, so the rules, my controlled qubits were individual qubits, but I have code blocks. So I need to get these individual qubits into the code blocks. And fortunately, in concatenated codes, that's not too hard. Actually, in most codes, that's not too bad. And one way you can do it is you can just kind of run the encoding circuit of the concatenated code with a little bit of error correction kind of interspersed. And this fails with a probability that's proportional to the gate error rate. And so I'm going to draw it something like this, where you should think of this as a single qubit, and then I get kind of an encoded code block at the end. And there's some noise now on the logical state of this thing. So the idea being is you're just going to send some time sequence of encoded data in some classical error correcting code. And then you're going to kind of use this gadget here to encode this into this computational code that I have my 1D fault-tolerant scheme for. And then I'm just going to run some logical level, like classical decoder on this time sequence to get my to recover from the noise that I introduced whenever I did the encoding. So this is kind of something that might look like. I've sent this sequence of bit strings where this is like a 7-bit code. And kind of this is kind of chunked up into frames, and I decode each frame into some logical value using this like classical decoder that I can implement using the gadgets for my 1D fault tolerance scheme. Okay, great. So in terms of how to implement this kind of in this model that I've built up, this part's a bit technical, so if you like, you can skip it. But the general idea is that we want to decode these frames. And so we have this time sequence of bits coming in. And then we also have this kind of metronome, which we can arrange for this to be produced for us noiselessly, where it just kind of marks off whenever each frame starts. And okay, so I need to be looking at a kind of a window of size the block length of my program code. So what I'm going to do is I'm going to kind of copy the value, kind of skip over one, copy the value, skip over one, and so on, such that I'm looking at a bunch of consecutive values of the kind of initial program sequence. And I know that I'm looking at kind of the correct frame whenever this kind of metronome is 1. And then I'm going to run my decoder from my classical code. And then I'm going to have a bunch of kind of message symbols. And if this value is 0, I'm just going to output all zeros. And if it's 1, I'm going to output the decoded value. Okay, great. And then I'm just going to recombine them. Whenever it's just by kind of doing the skipping trick again, and then just summing the result. If my decoder was looking at kind of, it's kind of, you can think of it as I'm looking at some sliding window of this program stream. If my decoder was looking at the wrong sliding window, then I know it's invalid because I get, some 0 or something like that. And whenever I'm aligned with the correct window, then I know it's valid and I can output it. And then this just gets me back to the full thing. And then the actual computation of this sort of metronome thing, you can do some kind of majority vote type thing that I won't get into. Okay, so that already suffices for a universal processor. So we have a memory. It's the same statement as earlier. And then we can do, we have this computation part. So we have a constant number of controlled qubits. The processor can be initialized to some arbitrary initial state. And we can compute the output of some circuit in some depth, which is quite large. It's kind of the total number of qubits in our processor times the total number of gates in the circuit. But we can do it. And kind of the reason why you can imagine this, I didn't quite touch on this, but in some sense, you have to wait for, because these qubits are kind of circulating along, you have kind of like a one-dimensional connectivity, and you kind of have to wait for them to come back around. And that's kind of the slow part. Yeah.
So say an arbitrary initial state, are you assuming all of the qubits can be put into some chosen initial state? Is that what you mean by that line?
No. So it doesn't matter what the initial state of the processor when I like walk up to it. It kind of self-initializes. We actually greatly simplified. This used to be a much more non-trivial statement because we had part of our construction we managed to remove, which is quite nice. Yeah. Okay. Yep.
So QEW, that's not how classical computers scale, right?
Say one more time.
Is that how classical computers scale?
Classical computers actually scale like this. So it's just the number of gates in the circuit.
How big is that?
Let me get back to that. Okay. So
was V the number of controlled qubits?
Yeah, sorry. V is the total number of qubits in the circuit, and V is the number of gates in the circuit, and W is the number of qubits in the circuit. So it's kind of the space times the overall gate count, which is quite bad. So let's speed things up.
Sorry. You said output of a polynomially sized circuit on W qubits with V qubits, or W.
Oh,
qubits?
V space-time. Yeah, V gates, yeah.
Sorry, V is the depth of the circuit.
Total gate count.
Total gate count.
Yeah, so in general, it can be width times depth. So it's quite bad. Yeah.
Also, like, so in some sense, in the memory part,
Yeah.
what you're doing is making some sort of QEC code of size only a polylog W factor
Mm-hmm.
with, I guess, a distance of omega W in some sense.
The distance.
From the first, I'm trying to understand this from the QEC language because
Yeah.
this logical error scaling kind of seems like it's kind of like N being W polylog W, K being W, and D being omega W.
Oh, there's a typo there. Sorry, one moment. Let me think. Yeah, so this should be, I think, polynomial expression W. Sorry about that. I just got off the plane yesterday, so I'm not quite ready to do this live. But yeah, it's sufficient. And the quantifiers are a little bit weird because the family is kind of independent of like the circuit you would like to run. But essentially, your tape, you should think of it as, and actually the width of the tape and the number of kind of the size of this thing is the width of this thing and kind of the length of the tape is not quite coupled so closely. So, but essentially you can change. You should think of the width as kind of setting the block length of the code that you're using, but you can use kind of every station along the tape to store like one code block. At least in the case where you pick that tape size to be very, very large, then you're in good shape. Otherwise,
actually, my question is more like using this part. It seems like I can construct a QEC code with N, NKD, N being W polylog W, K being W, and D being also omega W. So is it right, or is it actually quite different?
Yeah, so think of the distance as being, yeah, sorry, this should be, I think this got renamed from a variable. Yeah, this is like, this parameter here should be the width of the tape.
So lowercase w maybe?
Lowercase w, yeah,
Okay.
yeah. I think it got actually renamed from lowercase w, my bad. Yeah, so so you have exponential expression in the width of the ribbon, but then you can but you can use kind of all the positions. So in the other direction, you kind of only lose like a constant factor off your rate.
Okay.
And then you can maybe pick it to be like very wide, for example. Yeah, okay. Okay, so in terms of how to speed things up asymptotically, we had this data that was like propagating on this tape, and we have to wait for it to come back around. And kind of in some sense, there's kind of, at least apparently, some like signal propagation barrier kind of in terms of, in general, in the worst case, our operands could be kind of at distant parts in the chip, and then we have to bring them together, right? So I'd like to speed us up a little bit. And what I'm going to do is I'm going to extend our model of computation a little bit. And so I'm going to allow myself these like kind of classical wires, where what I mean by classical wire is something that I'm still required for it to be unit density, But I'm going to allow myself instantaneous classical signal propagation along this wire. So if I have, for example, 2 points on the chip, I set the wire to be 1, and then I kind of get the value 1 kind of instantaneously at the other side. And this is approximately what happens in classical computers. And that allows me to do some teleportation just because I can pre-share the entanglement and then use the classical signal propagation to communicate my fix-up operation. So kind of the way to do it is I can then construct a memory that's like teleportation based. You can think of what I just showed you as kind of sitting off to the corner here, where the memory tape is kind of picked to be kind of smallish. And then I have all these little cells. And the idea being is that they're just going to be doing constantly entanglement swapping. And then you're going to do some like, you're going to kind of start to teleport things into and out of the memory. And you're using the fast classical signal propagation in order to do that. And then the actual parity computation itself, you kind of forward that off to kind of something sitting over here, compute the parity, and then apply the fix-up. And so that gets you your runtime down from kind of this really nasty space factor down to something that's essentially information theoretically optimal. If I only have a constant number of bits, I need kind of, or a constant number of control lines, I need this number of bits to describe my program. And so kind of that's the best I can do. And indeed, this is the scaling that classical computers get. Sorry?
Do you assume you can measure it everywhere?
No.
Okay.
So the way you do this, so in terms of what precisely it means to have a classical signal in this model I've set up where I have quantum degrees of freedom everywhere, I do need a way of getting that qubit value into like a classical wire. And so that kind of needs some sort of measurement. Yeah, that's right.
Okay. So
Yeah.
everywhere.
Yeah. But importantly, I am kind of tracking the wire that I needed to communicate that measurement result. Yeah. Okay, great. So, okay, I said so asymptotically, this is essentially what your classical processor gets, but classical processors aren't very slow, and this looks pretty slow. So there's this bag of tricks from classical computer architecture that we can kind of do here. First off is that the instructions, I've kind of given a very, very minimal instruction set just for the sake of, because we can. But classical instructions in computer architecture do actually very, very complicated things, right? They might do, instead of apply an AND gate to the first 2 bits of some register, they do, take this 512-bit register, it's chunked up into 32-bit floating point numbers, and take a second one and just add them all, things like that, or just, so a single instruction might be specifying, some large number of like floating point multiplies or something like that, which is actually a very, very big circuit to be running, and it's described using a very short instruction. So we can do something very similar, you might imagine. The second one is we can pipeline operations. Kind of if we have in our program or in our quantum circuit, if there's many gates that are acting on kind of independent supports, we can execute those gates in parallel. And so you can do something like this. You can also imagine kind of multiprocessing. So if I have kind of classically, we don't run one processor, we actually run many processors, and frequently they have like some shared memory, right? So we have kind of these different cores acting on kind of different pieces of the circuit that we'd like to execute. And we could do something similar here. And then kind of your time overhead drops by that factor that you can do this if you can find enough work to keep this course fed. The second consideration is whether or not we can get kind of tight enough fabrication, unclear, or if we can't get tight enough fabrication, can we do some sort of local tune-up? The scheme itself is resilient to fabrication defects. That's kind of nice. And then really what we'd like to do is I describe some measurement-free fault-tolerant scheme, but really you'd want to have some classical degrees of freedom and do either classical fault tolerance or maybe your classical degrees of freedom are like good enough. And there are some technologies that where you could hope to achieve this. You might do something like shuttling instead of just explicit swaps. And then also this whole thing is kind of compatible with, for example, kind of various ways to get high rate concatenated codes. So you can imagine like a constant rate version of this scheme, and that's not so hard to achieve. With that, I'd like to conclude. Thanks.
Thanks for the talk. Any questions?
How like this is very long term, it's going to require new hardware stuff, but it seems like something a universal quantum computer could do fairly easily. So like what are the big changes to like hardware evolution that you think would be needed?
Yeah, so in order to scale, kind of the reason why you would want to do something like this is that it allows you to build a computer that just looks fundamentally different from what you're building already. So I'm being very wasteful with qubits. So you need to just build a lot of them, right? Kind of in some cases, like for example, like a neutral atom array or something like this, well, there's one issue that I don't know how to reload the tweezers in kind of an autonomous way. And in some sense, you've already kind of paid the price for having universal control in some sense. Not quite, but you're very close to it. So if I wanted to build an atom array with, say, 100 million atoms or something like that, that's something that's kind of difficult to do kind of for example, laser power considerations. There are tricks you can play, but so kind of I'm envisioning something like building something like a semiconductor quantum dot device or something like this, but you would need to be able to do everything locally or kind of do these shared controls, which is quite hard.
So, another question?
I wonder if you considered architecture work. You know, there are qubits and there's classical transistors running by them, so you control them. You know, and transistor would be.
Yeah, so this is why I like semiconductor quantum dots, because kind of you can fabricate a transistor right next to your dot, and that's like not a problem. The problem is that the transistor and the dot is about the same size. And so if you can imagine if you have a very dense grid of dots, actually what you start to run into is that your wire lengths, like the minimum separation between your wires is actually very, very close to the maximum separation of your dots. And that's quite problematic. Yeah.
So in your setup, you have a specific gate on each point in the space, right?
Mm-hmm. That's right.
And it's a kind of donut geometry.
Yeah.
And it's kind of circling around the donuts. And which gate to be applied in some sense is controlled by there's a control line that's like kind of sliding the swap gate, sliding your qubit through so control is determining some swap, and your qubit is going through some gate or the other.
Right. Right.
But is donut geometry like few control line really enough to make all the instruction? It's kind of hard to imagine.
So think of it as, so you have this background of this like depth 3 circuit.
Yeah.
And that's doing most of the actual operations, right? The error correction and all this sort of thing. You really just have to you can let it kind of do its thing, and every once in a while you kind of have to kind of say, okay, well, this qubit goes that way, this qubit goes that way, you know, whatever. And you only have to do that like a little bit.
So I guess maybe you already explained the control, maybe a slide 16 or something. Maybe can we go? Yes, up. The up further. Maybe.
Yeah, this one.
Yeah.
No, you had an example of 1000001. Next slide, maybe. No, the after. Oh, yes, this interface.
Yes. So-
Sorry, two slides after me. Sorry. Yeah. So this one, so this ST is like one of the control line, and that's propagating through the depths of the donut. Is it?
So think of this as something that's running off to the side that's giving you these control bits here, these kind of perfect control bits. Once you're happy with having these perfect control bits that are encoded in your code of your 1D fault-tolerant
Sure.
scheme, then kind of these three operations suffice in order to get universal computation.
So one line will only kind of connect it to the maybe two layers of like inside for the donut, inside of the donut. But through the sequence of it, this control line effect can propagate through the entire width of the donut, and that's how it's working.
Yeah, so think of it, okay, well, so instead of a donut, think of it as just a square.
Yeah.
And then I'm kind of, for the most of the square, I'm just kind of packing in some tape, some memory tape.
Yes.
And then I'm kind of augmenting it with this piece that's just kind of sitting right here or something like that. And then I need these controls. And so that's also some piece that's sitting right there or whatever, supplying the controls. And yeah, that's the processor.
So, but for the like quantum computer, this width is determining the number of kind of qubits that's doing the computation, right?
The width of the overall kind of this dimension or like this dimension?
This dimension.
Um,
So, maybe I can ask more.
okay, sounds good. Yeah.
Is the question like how do you address qubits the kind of spread across this?
Yes.
Okay. Yes, it's a time encoding. Kind of, I have to wait for the qubit that I'm going to perform the operation to come by, and then I send a 1 at the same time. Yeah.
But then that only goes to the qubit right next to the control line. What about like?
So the qubits, yeah.
Okay.
Yeah, they're constantly circulating on this tape.
Okay.
Yeah. And kind of this controlled phase and the Hadamard allow me to suffice to swap, and then I can implement like a 1D circuit.
So then the circulation time must scale with the width omega or lowercase w, right? There's a time overhead of like the circulation of the width.
It's the overall length of this tape.
Yeah.
There is some weak dependence on the overall, like the width as well. You need to make sure that you can actually pack it in, but yeah.
Can I ask about what's like the difficulty of making a high rate version of the concatenated?
It's not particularly difficult. I just
remove
the slide on it. Yeah, maybe in a second paper or something. There's yeah, I'm working on some people to do that, but it's the construction is what you would expect, which is you take, you take 5 papers and you just paste them together.
Is there any problem with like addressability? I feel like that could be the only thing.
If you're only doing asymptotics, then no. Yeah. And then you get a constant rate processor. Say one more time.
Is it possible to optimize tau parameter, or it is of the given parameter in that situation?
This tau parameter is really just how long you're running it. So kind of the failure rate kind of increases linearly with the runtime of the memory. So yeah, all I'm saying is that like kind of, I have some, my memory lifetime is my logical failure rate is kind of exponentially small in the width of this tape, but it grows kind of with the number of sites, so the overall length, and also the number of the how long I wait for my memory. Yeah. Go ahead.
Okay, so it's the time. Let's thank the speaker again.